Welcome to the deep dive. Feeling like your Rails app is sometimes stuck in molasses when hitting the database. We're tackling a core concept today that can be the secret sauce to snappier performance. Database connection pooling. Instead of your app constantly knocking on the database door, waiting for it to open, we're going to explore how Rails keeps some channels sort of pre-opened and ready for action.
Exactly. Think of it this way. Every time your application needs to talk to the database without pooling, it's like building a direct line from scratch.
Yeah.
That involves a bit of back and forth, some authentication. It all adds up. Connection pooling is about having a set of these lines already up and running, ready for instant use.
Right. So this deep dive will pull back the curtain on how Rails, through the magic of Active Record, implements and manages these reusable connections. We've got some really interesting details we've uncovered. Understanding this can be a real game changer for optimizing your Rails applications.
Absolutely. It's one of those foundational elements. Get connection pooling right, and you can see a noticeable improvement in your application speed and efficiency. It's really all about making those database interactions as smooth and quick as possible.
Okay, so let's get down to brass tacks. What's the scenario if we didn't have this connection pooling in our Rails applications? Like, what would happen every time we needed some data?
Well, without pooling, the process would be quite repetitive, kind of tedious, actually. For every single request hitting your application that needs to interact with the database, it would initiate a brand new connection.
Yeah.
Then it would perform whatever database operations it needed, fetching data, saving changes, and finally, it would close that connection down. Rinse and repeat for the next request.
And as we mentioned, setting up that connection isn't just a flick of a switch.
Yeah,
There's a bit of a process involved each time, right? Like it takes actual time.
precisely. The database server needs to verify the application's credentials, establish a secure communication pathway, and allocate specific resources just to handle that connection. All these necessary steps take a finite amount of time. So in a high-traffic application dealing with, say, numerous concurrent requests, this constant cycle of connection creation and termination can really become a bottleneck. It can slow everything down.
Okay, so connection pooling swoops in like a superhero to prevent all this repetitive work. How does Active Record actually handle this behind the scenes?
Active Record cleverly maintains a pool of these database connections. Now, a key thing to remember here is that this pool is specific to each web process, like your Puma workers, and each background process, such as your Sidekick workers.
Okay.
So the connections available to a Puma process aren't the same ones available to a Sidekick worker.
Right.
However, within a single process, all the threads running inside it can freely share the connections that are currently available in that process's pool.
Got it. So each of our web and background workers has its own dedicated stash of connections. What happens then when our application code actually needs to query the database?
Well, when a thread within one of these processes needs to execute a database query, it essentially borrows an available connection from its local pool. It uses that connection to perform the query, retrieve the results, and then, crucially, it returns that connection back to the pool.
Oh, okay.
This makes it available for other threads within the same process to use.
Now, I recall reading about a change in Rails, I think fairly recently, about how long these connections are held. Can you tell us more about that?
Yes, that's right. This is a really smart optimization that landed in Rails 7.2. Before this change, a connection would typically be reserved for the entire duration of a web request or the execution of a background job.
The whole time.
Yeah, the whole time. The potential downside here was that a connection could be tied up even if the application was just doing some other work, like, I don't know, waiting for an external API or performing some in-memory calculations and not actively talking to the database.
Yeah, that sounds like it could limit the number of actual database operations we could handle concurrently.
Exactly. So to boost concurrency and also to enhance how query caching works, Rails 7.2 changed this. Now, connections are leased and returned at the level of individual queries.
Oh, okay. Just for the query itself.
Right. So for each specific database query your application makes, it grabs a connection from the pool, executes the query, and then immediately puts the connection back. This allows for a much higher degree of concurrency because connections aren't held for extended periods when they're not actively being used for database I/O.
And you mentioned query caching being related to this change. How does that tie in?
Well, before Rails 7.2, each individual database connection in the pool had its own isolated query cache. Since a single request or job usually stuck with the same connection throughout its lifecycle, this was generally okay. However, with the new per-query connection handling, The query cache needed to be accessible across all the connections within a process's pool.
Ah, right, because you might get a different connection next time.
Precisely. Therefore, the query cache is now associated with the pool itself, meaning it's shared among all the connections within that pool.
That makes perfect sense. So how do we actually configure this connection pooling behavior in our Rails apps? Where do we tweak these settings?
The primary place you'll manage these settings is in your database.eml file. There are several key configuration options you should be aware of. The most fundamental one is the pool setting. This determines the maximum number of connections that Active Record will maintain in the pool for each of your application's processes.
Right.
By default, this is often set to be equal to your Rails max threads environment variable.
And you hinted earlier that directly equating the pool size to Rails max threads might not always be the best approach. Is that right?
That's right, yeah. While it's a common starting point, the assumption that each thread will always need a database connection simultaneously isn't always accurate, especially when you start considering asynchronous operations, which we'll definitely get into later. Just keep in mind that a simple one-to-one mapping isn't always the optimal strategy for your pool size.
Okay. What other important configuration options should we know about in database.eml?
Another crucial one is checkout timeout. This setting dictates how long a thread will wait to obtain a connection from the pool if all the available connections are currently in use. The default is typically around 5 seconds.
5 seconds, okay.
If a thread waits longer than this specified timeout period, it will raise that dreaded active record, connection timeout error.
Definitely an error we want to avoid seeing in our logs. Are there also settings for managing the connections within the pool over time, like cleaning them up?
Yes, absolutely. There's idle timeout. This setting defines how long a connection can remain unused in the pool before Active Record considers it eligible for removal. The default is often 300 seconds, so 5 minutes.
5 minutes.
Okay. This helps to free up resources held by connections that aren't actively serving any requests. Then we have reaping frequency. This setting determines how often a background process, often referred to as the reaper, runs to check for and remove these long idle or potentially dead connections from the pool. The default for this is usually 60 seconds.
The Reaper, it sounds slightly dramatic. What exactly is its role here?
Hey, yeah. Think of the Reaper as the sanitation crew for your database connections. It periodically wakes up based on that reaping frequency and examines the connections within each process's pool. It looks for connections that have become unusable for some reason. Maybe the database server had a hiccup or something, or connections that have just been sitting idle doing nothing for longer than the idle timeout period.
Right.
It then removes these connections from the pool, ensuring your application isn't holding on to resources that are no longer needed or functional.
So idle timeout is the criteria for saying this connection is past its prime, and reaping frequency is how often the cleanup crew comes around. Makes sense. Are there situations where we might want to adjust these reaping frequency or idle timeout settings?
Yes. If your application tends to experience sudden spikes in traffic, followed by periods of relative calm, you might want to consider lowering both the reaping frequency and the idle timeout.
Oh, okay. Why's that?
Well, this would make the Reaper run more frequently and remove idle connections more aggressively. The idea here is to ensure that during those quieter periods, you're not holding on to a large number of idle connections that might then become a bottleneck or just waste resources if a sudden surge of traffic hits. You clean up faster.
You mentioned that idle connections can be potentially problematic. Why is it that we don't just want to have a huge pool of connections open and waiting all the time, just in case?
That's a great question, and it touches on a common misconception. While it might seem like having a large pool of readily available connections is always a good thing, excessive idle connections can actually negatively impact your database performance.
Oh, so?
Well, the first key reason is memory consumption on the database server itself. Each database connection, even when it's sitting idle, consumes a certain amount of memory. This memory is used for things like maintaining session state, internal buffers, tracking the connections, stuff like that.
Right.
If you have a large number of idle connections, let's say 100 of them, and each one uses even a modest amount of memory, maybe 10 megabytes each, that quickly adds up to a gigabyte of RAM being used just for inactive connections.
Wow. Okay, yeah, that can really eat into your resources. What's the other downside of having lots of idle connections?
The second significant issue is CPU overhead on the database server. Even though these connections are idle from the application's perspective, the database still has to perform some level of maintenance on them. This can include things like sending keep-alive packets to ensure the connection is still active, managing its internal tables of active processes, things like that.
Yeah.
The important thing to realize is that this overhead doesn't always scale linearly. As the number of idle connections grows, the database can end up spending a significant portion of its CPU cycles just managing these connections instead of actually processing real queries.
Ah, I see.
That's why the Reaper's role in cleaning up these idle connections is so important for overall database health. It helps mitigate both the memory and CPU issues.
Okay, so effectively managing our pool size is crucial. How can we estimate the maximum number of connections our web and background processes might actually need? Let's start with the web processes, like Puma.
Right. For your web applications, typically running with Puma, each Puma worker process will have its own independent connection pool. Remember that. Within a single Puma process, each thread can, at most, check out one database connection at any given time.
Okay.
Therefore, a reasonable estimate for the maximum number of connections needed per Puma process is usually equal to the max threads setting in your Puma configuration.
Right, one connection per thread, potentially.
Potentially, yes. So to get the total potential connections for your entire web tier, you would multiply the number of your web dynos, or instances, by the number of Puma processes running on each dyno, and then multiply that by the max threads value.
Makes sense. And what about our background processing, like with Sidekick? How do we estimate there?
It's a similar logic. Sidekick also operates with separate processes, each with its own connection pool. The concurrency setting in your Sidekick configuration determines the number of threads each Sidekick process uses. And thus, that concurrency value is the maximum number of connections that process might need concurrently. So to estimate the total potential connections for your background workers, you'd multiply the number of your worker dynos by the number of Sidekick processes per dyno, if you're running more than one, and then by the concurrency setting.
Okay.
Just a quick note, if you're using something like Sidekick Swarm to dynamically manage your Sidekick processes, you'll need to factor that dynamic scaling into your calculations, which can be a bit trickier.
Good point. So at a minimum, our database needs to be able to handle the sum of these potential web connections and potential background connections.
Exactly. And it's a really important point to remember that if you have pre-boot enabled for your application deployments, which is a common practice on platforms like Heroku, the maximum number of connections you might need can temporarily double during the deployment process.
Double. Why is that?
Because for a brief period during the release phase, both your old set of dynos and your new set of dynos are running simultaneously, and both will be establishing connections and drawing from the database. So you need capacity for both sets at that peak moment.
No, okay, that's a critical detail. Now, you mentioned LotusSync earlier, the asynchronous query execution feature in Rails 7. How does that impact how we think about our connection pool needs?
Right, LotusSync. This feature allows you to offload the execution of database queries to background threads, so the main request or job thread isn't blocked just waiting for the database. The way these asynchronous queries are handled is configured using config.activerecord.asynqueryExecutor.
Okay.
You have three primary options here. Nil, which basically disables it, makes LotusSync run synchronously. Then there's .global thread pool, which uses a single shared thread pool for all async DD operations within that process.
And the third?
And the third is .multi-thread pool, which interestingly creates a separate thread pool for each individual database connection in your main pool.
Okay, so if we're leveraging LotusSync, we need to consider that these additional background threads might also be vying for database connections from the same pool.
Precisely. And Rails provides another configuration option called Global Executor Concurrency. This has a default value of 4.
4.
This setting limits the number of concurrent asynchronous queries that can run per process when you're using either the .global thread pool or the .multi-thread pool executor.
Right.
So when LotusSync is active, the calculation for the maximum number of connections a single process might need changes. It becomes the process's main concurrency level. So max threads for Puma or concurrency for Sidekick LUS, the global executor concurrency value.
Plus the async threads.
Exactly. Plus the async threads capped by that concurrency limit, and then you add one more.
Plus 1, what's the extra one for?
That plus 1 is typically to account for the main control thread within the process.
Yeah.
It might occasionally need a connection itself for tasks like schema loading or model introspection, things outside the normal request job flow.
Wow, okay. That definitely adds a layer of complexity to figuring out the ideal pool size when LotusSync is in play. It's not just threads anymore.
It really does. Thankfully, there are some helpful resources out there. For example, the folks at Judascale have put together a calculator online that can assist you in estimating the maximum number of connections your application might require. It takes into account factors like LotusSync and your various concurrency settings.
That sounds useful. Okay, let's shift gears and talk about actually setting the pool size in our database.eml file. We often see it configured like this pool board person, env.fetch, Rails max threads, 5%. Based on our discussion, just mirroring the number of threads might not always cut it, especially if we're using Lotus Sync, right?
That's absolutely correct. While using Rails max threads is a common and often reasonable starting point, it doesn't inherently account for those extra connections potentially needed by the asynchronous query executor we just talked about.
So what's a better approach?
Well, a simpler and often more robust approach is to directly set the pool size to the maximum number of concurrent connections that your specific database plan actually supports.
Just set it to the max the database allows.
Yeah. For instance, if you're using, say, a Heroku Standard Zero database plan that allows up to 120 concurrent connections, you can simply set your pool size in database.aml to 1 in 20.
Even if our application, like our Kuma threads plus Sidekick threads, doesn't add up to 120. Even if we calculate a much lower need.
Yes, exactly.
Yeah.
And the reason this works well is because Active Record initializes database connections lazily.
Ah, lazily, okay.
This means that your application will only establish the connections it actually needs at any given moment, up to the maximum limit you've configured in the pool setting. It won't just create 120 connections right at the start if they're not needed.
So you don't need to be overly conservative with that number.
Right. You're not penalized for setting it high, other than allowing the potential for higher usage. The key is simply to ensure that your estimated maximum actual utilization, considering web processes, background processes, Lotus Sync, maybe that deployment overlap we talked about, doesn't exceed the hard limit imposed by your database provider. Setting the pool to the max just gives you headroom.
Okay, that makes a lot of sense. Now, you also briefly mentioned PG Bouncer earlier. What exactly is that, and how does it relate to Active Record's built-in connection pooling?
Right, PG Bouncer. It's a lightweight external connection pooler, specifically designed for PostgreSQL databases. It acts as an intermediary, basically sitting between your Rails application or multiple applications and your PostgreSQL database server.
Okay, so it's like a proxy.
Kind of, yeah.
Yeah.
The crucial difference between PG Bouncer and Active Record's internal pooling is the scope at which they operate. Active Record, as we've discussed, manages a pool of connections within each individual Ruby process.
Right, per process.
PG Bouncer, on the other hand, manages a single pool of connections that can be shared across all of your application processes, all your web dynos, all your background workers, everything connecting to that database through PG Bouncer.
Oh, interesting. So if we have multiple web servers and multiple background job processors, PG Bouncer can provide a unified pool of database connections for all of them to draw from.
Exactly. This can be particularly beneficial in high concurrency environments where the sum of all the per-process connection pools from Active Record might result in a very large number of direct connections hitting the database server itself. PG Bouncer can help to reduce the overhead on the database by multiplexing connections. It essentially takes many incoming client connections from your app instances and funnels them through a smaller number of actual persistent connections to the database.
That sounds powerful for larger setups. Okay, now let's talk about that dreaded Active Record connection timeouter. We've mentioned it a few times. What does it really tell us when we see that pop up in our logs?
Yeah, nobody likes seeing that one. This error is raised when a thread tries to check out a database connection from the pool, but is forced to wait longer than the configured checkout timeout period.
And why is it waiting?
It's waiting because all the connections in that process's pool are currently checked out and in use by other threads. There are none available.
Okay.
A very, very common cause of this is simply having a pool size that is too small relative to your application's concurrency within that process. For example, if you have Sidekick configured to run with a concurrency of 10, but your connection pool size is only set to 5 in database.eml, then if more than 5 Sidekick threads try to access the database simultaneously, the 6th, 7th, etc., threads will have to wait.
And if they wait longer than 5 seconds?
Exactly. If they wait longer than that default 5-second checkout timeout, boom, you'll see that error.
So a primary step in troubleshooting this error is often just to increase the pool size, maybe using that set it to the database max strategy we talked about?
Yes. In many cases, simply increasing the pool size to a sufficiently high value, perhaps up to the maximum your database allows, can resolve these timeout errors. However, it's important to note that even with a seemingly adequate pool size, you might still occasionally encounter these errors. There are a few less obvious scenarios that can lead to connection starvation.
Such as, what are some of these less obvious culprits that might trip us up?
Well, one common issue I've seen is when you have custom code within your application that explicitly spawns new threads and then performs database queries within those newly spawned threads.
Ah, like using thread.new inside a service or something.
Exactly. Remember that these newly created threads exist within the same process, so they will also draw connections from that same process's connection pool.
Hmm.
So if you have, say, a service object that, for example, creates 5 new background threads to do some work, and each of those tries to execute a database query concurrently, they could quickly exhaust the available connections in that process's pool, even if your main Puma or Sidekick threads aren't under particularly heavy load at that moment.
That's a really good point. We need to be mindful of any background-like processing we might be doing within our main web or worker processes, as that could be consuming extra connections unexpectedly. Are there any other surprising ways we might be using more connections than we realize?
Yes, active storage, specifically when configured to use proxy mode for serving files, can also contribute to increased connection usage.
Active storage, how?
When a request comes in for an active storage file and is being served through the proxy controller, instead of redirecting to S3 or another service, Rails actually utilizes 2 separate threads internally to handle this.
2 threads for one request.
Yeah, one for the main request handling and another specifically for the streaming of the file content back to the user. Each of these threads will typically require its own database connection from the pool, often to look up metadata or permissions.
Interesting. I definitely wouldn't have immediately connected active storage proxy mode to potential connection pool exhaustion. What about rack timeouts? You hear about rack timeout gem. Can that play a role in these errors?
They certainly can, indirectly. Rack timeout is often used to automatically terminate web requests that are taking too long to process, which is generally a good thing to prevent server resources from being tied up indefinitely.
Right.
However, the way it achieves this, often by using Ruby's thread hashtag raise API to forcefully interrupt the request thread, can sometimes interfere with the proper cleanup of a database connection if that timeout happens while the thread is right in the middle of a database operation.
So the request gets killed.
But the connection might not be properly returned.
Yep.
Yeah, this can potentially leave the connection in an unclean state and still marked as in use by the pool, even though the original request that checked it out has been terminated. It becomes a sort of zombie connection taking up a slot.
Oof. So even though the request is cut short, the database connection might not be immediately released back to the pool. That's definitely subtle and something to be aware of. If we are seeing these timeout errors, and maybe just increasing the pool size didn't fix it, how can we go about investigating and figuring out the root cause?
A really valuable technique for debugging these issues is to log detailed connection pool information right into your error monitoring service whenever an active record, connection timeout error, actually occurs.
How do we do that?
Well, Rails provides a handy config before notify hook if you're using something like Honeybadger or Sentry or Bugsnag that you can use to attach additional context to your error reports just before they're sent. By including information about which threads were holding on to connections at the exact moment the timeout happened, you can gain crucial insights.
What kind of info can we get?
There are methods on the connection pool object, like detailed connection pool info or similar, that can provide a snapshot of the connections in the pool and, crucially, identify which specific threads currently own them. You'll see thread IDs and maybe some context about what that thread was doing.
Ah, okay.
By examining this output in your error logs over time, you can often start to see patterns. For example, if certain Puma worker threads or specific Sidekick job threads consistently appear as holding connections for unusual long durations right when timeouts occur.
That sounds like a vital debugging step, getting that context right with the error. Are there any proactive measures we can take to just keep an eye on the health of our connection pool before errors happen?
Absolutely. Proactive monitoring is key here. It's highly recommended to periodically send connection pool statistics to an application performance monitoring APM tool like New Relic, Datadog, Skylight, etc.
No.
You can use a gem like Rufus Scheduler or even just a background job that runs on a regular interval, say, every minute or even more frequently, to collect data directly from activerecord.base.connectionpool.stat.
And what stats should we send?
Things like the total size of the pool, size, the number of connections currently busy or connections, the number currently idle or available, and maybe the number waiting. You can then send this data as custom metrics to your APM. This will allow you to visualize the health and utilization of your connection pool over time through graphs in your APM dashboard. This proactive monitoring can help you identify potential bottlenecks, like maybe the pool is consistently near capacity, or spot issues like connections not being released properly, often before they actually lead to user-facing errors and service disruptions.
This has been incredibly informative, seriously useful stuff. So, just to quickly recap the main points, active record connection pooling is fundamental for efficient Rails applications. It works by reusing database connections instead of creating new ones all the time.
Exactly. And it operates on a per-process basis.
Right. And we need to carefully consider those configuration options in database.aml, especially pool, checkout timeout, and idle timeout, and understand how they interact with the concurrency settings of our web servers like Puma, Max Threads, and background workers like Sidekick concurrency.
Precisely. Understanding the total potential connection demands of your application, especially if you're using modern features like Lotus Sync, which adds its own threads, is absolutely key to configuring an appropriate pool size. And it's also crucial to be aware of how seemingly unrelated parts of your application, like, custom threading you might add, or even using active storage in proxy mode,
Huh.
can indirectly impact your connection pool usage.
And if our application's needs sort of outgrow active records per process pooling, maybe because we have tons of processes, or if we're just constantly bumping up against connection limits on our database plan,
Yeah.
then something like PG Bouncer offers a powerful alternative for managing database connections at a broader system-wide level, sitting between the app and the DB.
Exactly. It's another tool in the toolbox for scaling. And finally, if we do encounter those frustrating active record, connection timeout, or exceptions, having a solid understanding of how to gather more detailed context through logging that pool status.
Right. Logging the detailed connection pool info.
Yeah, and actively monitoring our connection pool statistics over time with an APM. Those things can be invaluable in diagnosing and resolving the underlying causes rather than just blindly increasing the pool size.
So, for everyone listening, now that you have hopefully a deeper understanding of how Rails orchestrates these database connections behind the scenes, take some time to reflect on your own application's specific workload and concurrency patterns. Could fine-tuning your connection port configuration, maybe adjusting idle timeout or just setting pool to your database max unlock some hidden performance gains? Or perhaps exploring PG Bouncer is the next logical step to really optimize your database interactions at scale. It's really all about understanding the unique demands of your application and not being afraid to delve into these core performance considerations. Thanks for joining us for this deep dive.